Okay, so here we have a number theory question, right? And I'm joined by my beautiful assistant Mito here. And here we're supposed to determine the number of pairs A and B of positive integers, with A being less than 100 and B being less than 100, such that 324 multiplied by 2 to the power of 2A plus B multiplied by 3 to the power of A plus 4B is a perfect fifth power, right? So if you want to take a screenshot of this question or read it one last time, anything, etc., you should do so because I'm about to erase it, right? So here we have our question isolated, right? So 324 multiplied by 2 to the power of 2a plus b multiplied by 3 to the power of a plus 4b is equal to a perfect fifth power, which we just wrote as x to the power of 5, correct? So let's actually write this number in its primes, because I believe its primes have a base of 2 and a base of 5, meaning we can just simplify everything and get rid of this. So the primes of 324 is 2 to the power of 2 multiplied by 3 to the power of 4. So let's just simplify everything, meaning 2 times to the power of 2a plus b plus 2. We add this 2 because 324 can be written in the terms of 2 to the power of something multiplied by 3 to the power of something, and that 2 is to the power of 2, and multiplying the bases will add the powers. So 2a plus b plus 2 multiplied, and we do the same thing with the base 3 to the power of a plus 4b plus 4, and this is equal to a perfect fifth power, right? Now let's look at this. What do we notice here? These powers must be multiples of 5 to give us a perfect fifth power once we multiply everything. Isn't that correct? Yes. So these powers must be multiples of 5. Now, how do we display this, right? How do we show this? What do we do here, right? Now, we have something called congruent modular equations. We can display that something is a multiple of 5 using congruent modular equations. So I'll do that, and I'll show you how to handle these equations, and you'll know soon enough that solving this is pretty simple, right? So let me write the modular equations and remove everything else to make it simpler, right? Okay. So we have that a plus 2a plus b plus 2 is congruent to 0 mod 5. What this means is that this number, mod 5, so this number divided by 5 will give us a remainder of 0, right? This means that this number is a multiple of 5. Pretty simple. Now let's do the same thing with the other power, which was a plus 4b plus 4, which is congruent to 0 mod 5. Now let's deal with the first equation. Let's deal with the first equation first, right? So what we want to do here is isolate this b, right? So 2a plus b is congruent to negative 2 mod 5. Now, a little trick that we have with congruent modular equations, and in general, we really don't like having negative numbers in our modular equations. So what we can do is add 5 to this number until it becomes positive. Now the reason we can add 5 is because 5 mod 5 is 0, because 5 divided by 5 will leave us with a remainder of 0, correct? So let's add 5 to this negative 2, which will give us 3. So 2a plus b is congruent to 3 mod 5. Isn't that correct? So let's isolate this b. So b is congruent to 3 minus 2a mod 5. Now, I want to show you something before we move on. Let's say we have 7 mod 5. What will this give us? 7 divided by 5 is 1, remainder 2. Now, the mod function basically returns the remainder. So the remainder is 2. This will return 2. Now, how could we write 7? How could we make 7 the subject? We can write 7 by saying 7 is equal to 1 times 5 plus 2. Now, the reason we can say this is because 5 goes into 7 once, meaning there's 1 5 inside 7, and the remainder is 2. So by saying that 7 is composed of 1 5 plus the remainder, which is 2. Now, we can actually do this with this, but to do these with the variables, we have to isolate the variable, right? The variable that we want to express in an equation, we must isolate that variable. Now, let me just remove this here. This was just to help you guys understand. That's all. So, let's write an equation for b. So, b is equal, right, to... Oh, our little helper Mito wants to leave already. Let me just take her. Say goodbye to Mito. Bye-bye, bye-bye. And there he goes. Right, so b is equal to, let's use k, right? So k, 5k, plus the remainder, which is 3 minus 2a. Now, k is just an integer, right? K is just an integer number. Could be 1, could be 2, could be 3. Just an integer number. I think, yeah, it could even be 0, right? So, here we have an equation for b. Now, what do we do with this equation, right? How about we substitute this equation into our second congruent modular equation? Because what we call these two equations is a system of modular equations. This means that they work in harmony, they work together, they're simultaneous, right? It's a system. That means that we can just solve them by doing simultaneously. We can solve them simultaneously, basically, but we just have to follow the rules of congruent modular equations. So we can just substitute this b into this b right here. Now, what we would get is a plus 4 times 5 is 20, 20k. 4 times negative 2 is negative 8, plus 1, so it's negative 7, so let's put a negative 7 here. And 4 times 3 is 12, plus 4 is 16, so let's put a plus 16 here, and this is congruent to 0 mod 5, correct? So what can we do here? 20 is actually congruent to 0 mod 5. Now, the reason this is because 20 divided by 5 is just 4 with a remainder of 0. So we can actually get rid of this entire variable right here, right? Because 20 is just 0 in the terms of mod 5. So let's get rid of this variable. We already got rid of it. Let's just write a 0 here, right? So this means that negative 7a is congruent to negative 16 mod 5, correct? Now, here's the thing. We don't like negative numbers, remember? Negative numbers are a big no-no. We hate negative numbers here. Negative numbers can just leave the room. We don't want them. So what can we do? We can just keep adding 5 till the negative number goes away. Now, we can actually also do this with the coefficient of a here, right? So in the end, we will get, so 7 plus 5 will give us 3. So 3a is congruent to negative 16 plus 5 plus 5 plus 5 plus 5 will give us 4. Congruent to 4 mod 5. Now, we want to create an equation for a here. However, we can't do that quite yet because a is not isolated. There's a 3 next to it. Now, some of you, I'm not saying all of you, some of you would just go by it by just dividing by 3 on both sides. You cannot do that. Now, the reason you cannot do that is because with congruent modular equations, if this number is not divisible by this number, you can't divide. And it obviously isn't, because 4 over 3... is 4 divisible by 3? I don't think so. So what we have to do here is multiply both sides by the modular inverse of 3. Now, how do we get the modular inverse of 3? Let's go over to this small board here so I can explain it. So to get the mod inverse, so let's just write that as mod negative 1 of x mod n, right? It is equal, let's say it's equal to y, where x times y is congruent to 1 mod n, right? So here we have 3 mod 5, right? So what's 3 mod 5? So 3 is congruent to 3 mod 5. We want 3 to be congruent to 3 1 mod 5, right? So let me just write that here. So 3 is congruent to 3 mod 5. But we want to make this 1. So what number would we multiply 3 by to get this to be 1? 2, correct? Because 2 times 3 is 6, and 6 divided by 5 is 1 remainder 1, which will leave 1 here. So we can put a 1 here, and 2 times 3, which is 6, correct? Now, so the modular inverse of 3 is just 2. So if we multiply both sides by 2, what we get is, we get that 6a is congruent to 8 mod 5. Isn't that correct? That is pretty correct, right? So 6, right, is congruent to 1 mod 5, meaning we can just write this as a 1. Or let's just say by subtracting 5, and we said that subtracting or adding 5 is basically like subtracting or adding 0, because 5 divided by 5 leaves a remainder of 0, right? So you can just write it as a. And 8 mod 5, we can just simplify this by subtracting 5 here as well. So a is congruent to 3 mod 5. And now that a is isolated, we can write an equation for a the same way we wrote an equation for b, can't we? So let's just say a is equal to, instead of k, let's use m, right? So 5m plus the remainder, which is 3. Perfect. Now we can get how many pairs of a are, how many values for a are possible. Let me erase all this jibber jabber over here. Let me just erase everything. Okay, here we go. So a is equal to 5m plus 3. And we know that a and b are less than 100. So what's the maximum value possible here? Well, let's see. 100 minus 5 is 95. 95 plus 3 is 98. So the maximum value for a is 98. That means that the maximum value for m, let's write it as m, so, or m max, let's say m max, is equal to 98 minus 3 over 5, which is equal to 19. So the maximum value for m is 19. And here's the thing. We can't say that that means the values of a that are possible is 19, because what if m is 0? So m could be 0, 1, 2, 3, 4, 5, 6, 7, all the way to 19 inclusive, meaning that there are actually 20 possible values of a. So 20 possible values for a. Now let's write that on this small board here, so we can just like keep it in mind, or like keep it stored somewhere. So we have 20 values of a, and we're gonna multiply this with the amount of possible values for b to get the amount of possible pairs. So let me erase all this here, and I'll keep the little a equation here because we will still use it. Right. So if we remember correctly, b was congruent to 3 minus 2a mod 5. Why don't we substitute a here into this? Because remember, this is a system of congruent modular equations. They work in harmony. We can just substitute stuff in, and it's pretty beautiful, isn't it? So let's substitute this in. So we get that b is congruent to 3 minus 10m, and then negative 2 times 3 is negative 6, so we can just put a negative right here and put a mod 5. Now 10 mod 5 is just 0, because 10 divided by 5 leaves a remainder of 0, meaning we can just get rid of this variable completely. So let's get rid of this variable right here. And if you remember correctly, we don't like negative numbers. Get out of here, negative number. So let's add a 5 here, meaning that negative 3 turns into 2. And we get that b is congruent to 2 mod 5. Why don't we just do an equation for b? Because b is already isolated, isn't it? So b is equal to, let's use z. So 5z plus the remainder 2, right? Now b has to be less than 100 as well, if we remember the question correctly. So the maximum value for b that is possible is 100 minus 5 plus 2, which is 97. So the max value for z is equal to 97 minus 2 over 5, which equals 19. And remember, we said z could be 0. So z could be 0, 1, 2, 3, 4, 5, 6, 7, all the way to 19 inclusive. Meaning that the maximum, the maximum values possible for b is 19 plus 1, which is equal to 20. Now let's go over here. So the maximum possible values for a is 20. Maximum possible values for b is 20. And this equals 400 pairs. Right? That is our answer. We are done. Thank you for watching the video. I hope you learned something, at least how to manage congruent modular equations. It was a pretty fun number theory question. Pretty simple too, but it's a start. It's a start to this YouTube channel, and it's also a start to learning congruent modular equations. I hope you guys enjoyed the video. Thank you for watching, and bye.